It's my pleasure to introduce Dr. Marouane Salhi from Qubit Engineering. He is the CEO and co-founder of this company, and he also is the co-founder of another company called Creative Destruction Lab.
So I'm more like actually a member there.
Okay. Okay. Well, and he holds several degrees in applied and computational physics, a BS from I have to read this one. From Tunis in El Manar.
Yes, that's
El Manar. An MS from Wayne State University and a PhD from UTK. He's also worked for the U.S. Army Research Lab, and he's done a postdoc at ORNL, so he has lots of really cool experience and is currently working at the cutting edge of a really interesting field, which is quantum computing. So thank you for being here.
Thank you for the invitation. So it's really my pleasure to present the work that we do and the field, actually, not much of the work that we do, but mostly the field that we're doing. And I don't know if you had any quantum physics class before. There is a little bit of stereotyping about quantum physics in general, but it's not very easy to comprehend or kind of to assimilate, which I'm totally disagree. I totally disagree with that. And my main topic or the main message I want to introduce to you is what is quantum computing. And to get to quantum computing, we need to know quantum physics. And actually, quantum computing is just the engineering side of quantum physics. So basically, putting quantum physics to work for us in a way that we can use it for computational work and beyond just computational work. So the field is quantum computing. That's my main message. But what I'll focus on is these interesting phenomena in quantum physics. Okay, so that's why my title is actually unlocking potential of quantum physics for to understand or to actually build the future of quantum computing and beyond that. So the whole story started over 100 years ago when physicists started to investigate the element or what makes matter. What I mean by that, molecules, atoms. They're trying to understand the physics behind it, and they stumbled into some experiments that they couldn't explain. And it's said for some time that they couldn't understand that, but many experiments have been accumulated, and they needed some kind of new understanding or new concept, new way of thinking to understand. And one of these experiments is that as soon as they started to manipulate elementary particles or to interact with elementary particles, just like atoms, electrons, molecules, they noticed strange things. For example, as I'm showing here, is if you actually generate an electron beam using this electron beam gun, you will see that these electrons will behave almost like we have like waves. So they already know what's waves. Then we know the interference of waves. Are you guys familiar with waves in general? Probably seen mechanical waves. There's electromagnetic waves. And now we're talking about an aspect of a wave aspect for particles. That was very strange. In the sense, so there is this experiment. This is for electromagnetic, you can think of it, or even mechanical wave. And we can see this pattern of interference. That's something we totally understand in terms of it's a superposition of two waves. Wave, you can think of it as an excitation or of, let's say, the surface of the water if you throw rocks. And then you can see this pattern of interference. Now, what they've seen, the observation is that you can see the same pattern using an electron. So if you think of it, we have an electron gun. That means we have some electrons. It's like just you're sending these particles one after the other. And then what you see on the screen, their impact on the screen, is actually distributed in a very similar pattern, interference pattern, just like mechanical waves or electromagnetic waves. So how do these electrons know where to place themselves? Why do they actually distribute or choose to have an impact in this kind of distribution? That was very intriguing, and it's still a very, very interesting phenomenon that people may have different kind of interpretation for it. The way we describe it now, we call it the duality wave particle behavior in matter. So basically, we start kind of accepting that we need to associate a wave equivalence or a wave aspect of particles. That means particles who are objects, which we are used to think of them as any macroscopic object that we have. They have a momentum, they have a speed, they have mass. Now we need to think of them also as waves. So this is how the whole kind of concept started. And now that we're thinking of these this aspect, we kind of have to accept it because experiments is showing that. And until Einstein came up with this explanation of the photoelectric effect. Are you guys familiar with the photoelectric effect? This is how we're generating electricity from solar panels. Basically, you have an incident light, right? Electromagnetic wave. It excites the surface of the metal, and then some of the electrons will absorb that energy, and they generate kinetic energy, and they basically create electricity. That's a kind of concept. Now, even that phenomenon wasn't very clear because people always assumed that light is electromagnetic wave. So how can it excite a single particle? How can it? So now, at that moment, Einstein came up and said, actually, light is made of particles. So now again, we were talking about particles to be associated with waves, and now we're talking about waves actually made of particles, photons. So when even he introduced that idea, it was a little bit of, a discussion in there, but it was the only way to explain the effect that we see. And that's how now we're using this, solar energy as a source of energy, So I'm showing here an example. So this picture here is I'm showing the corresponding wave function of the hydrogen atom. And you can ask me, okay, well, what are these different, now states? And I'll go through what are states. So you can think of them as the mood of the hydrogen atom. We may be happy. We have a face where we're happy, we're angry, we're upset, we're tired. Different kind of states. That's exactly that kind of corresponds to what happens to the hydrogen when it has different levels of energy. So that corresponds to different states. Now, the same thing for waves. We can look at them as particles also, and this is why now we're totally talking about two aspects of the same thing. I like the other two pictures that kind of show this is an artistic work that people trying to imagine how a particle is a particle. So the particle is simple, but it's also a wave kind of like. Now that we accept that we have this aspect, we need to rethink a lot of the physics that we do. And there are consequences when now we're talking about particles to be waves, that kind of, introduce new things to us. And one of the things that we can accept about waves is superposition. I mean, you can see these two ducks, they're going on the water, and you can see that there is an interference pattern here. It's a superposition. That's something that we accept normally. But now when we go back and think about particles, and we think that particles already are waves, does that mean that they can superpose? Superposing basically as if I can have two cups at the same position at the same time. So, which is, I mean, macroscopically, we don't really accept that. We don't see it. We've never seen it at our level. But at the atomic level, at the microscopic level, that's where the law of quantum physics actually happens. And that happens. So superposition is and now we can have two incoming particles, which are also represented by waves, to superpose. They may even combine to make a new particle. So it's totally a different dimension now that we need to think of. So this picture that I'm showing here, this is from a research in particle physics. I think this is one of the pictures of the particle accelerator in CERN, Europe, where they basically try to accelerate elementary particles and collide them. So when you actually accelerate, you can elevate their energy, and you get into this position where they're more of a wave, kind of less of a particle, but with that much of energy. And in fact, what could happen there is some of the incident particles will totally annihilate. They will disappear to form a new particle. And this kind of makes sense because we think of it as a superposition of two waves that superpose to make a new wave, a new particle, a new state. And that's what they're trying to do. They're trying to see if they can find new particles. They can actually, discover new particles. And by combining different kind of particles, different kind of energy levels, and so on. So this is the first feature that we're getting from quantum physics, is the superposition. Now, entanglement. So this is a new concept. We don't really see it in our daily life, but you can think of it as some kind of unconstrained connection between two objects, or unlimited connection between them. That means wherever these two objects or these two particles are, doesn't matter how far they are from each other, or when, they will always be correlated. They will always feel any change that could happen to one of them. And this is not something that we can. This is something that we are actually producing and generating. We have now experiments, even here at Oak Ridge, where they can generate entangled photons. Photons are also, elementary particles. They obey the law of quantum physics, and we can make entangled photons. So it is a very interesting concept. It's new, and it's also very useful. So you can ask me, how can we use, what is it about this entanglement? And I can tell you, it's being implemented now as we speak in security, in quantum cryptography. And it's in which way? Basically, you know that if you generate two entangled photons, if someone tries to alter or measure any information carried by one of the photons, the other photon will feel that, will detect that. And that means if I send you a photon that is entangled and I keep one at the lab, if you try to change, if someone try to kind of intercept that photon or try to alter or read the information that's carrying it, I will notice that at the lab. So it's a very, interesting way of developing a new security, new technology for cryptography. There is another concept that is associated with quantum physics, is quantum tunneling. So quantum tunneling is basically the possibility of going through energy barrier. This is something that we cannot accept at our macroscopical level. So going through a wall is an impossible thing that we can do, right? But think of this barrier of energy as a particle. That means that barrier also has some kind of wave-like aspect. And we know that waves can actually go, they superpose and they can actually overlap and they can keep going. So, and that's why in some of the experiments, they were expecting a wave, an incoming wave, to be reflected, to go back. But then they noticed that there is some measurements. They can actually detect the wave beyond that barrier. So the only explanation for that is that we had tunneling. Now, so these different observations or these different phenomena that people seen this required some kind of mathematical reason, some kind of understanding. Why is that? And that's how quantum mechanics was born. So people tried to develop this science, And in fact, quantum physics was built on equations that describe these behaviors, and the solution can only be a wave function. So mathematically actually corresponds and kind of match what we've been seeing, what we've been observing in experiments. You know? So what we talked here about, we talked about tunneling, we talked about entanglement, and we talked about superposition. Right? So these three concepts that will be the basis of future technology, the future quantum technology. Any questions so far? So the whole idea of quantum computing is, can we actually use these interesting phenomena to do something like the cryptography? And to get there, we have to build a concept, and we need to kind of adapt ourselves to the concept of a wave function or even states. What we described about the hydrogen atom here, the states, this is how we're going to describe now everything around us, some sense. And that means for any physical system, we will associate a state. And that state can change, can go from one to the other by operation or mathematical operators that we apply on these states. And that's how we're going to describe everything around us. So have you, so the mathematical frame for quantum physics is basically linear algebra. And the states will be described by a vector. The to change from one state to the other will be described by operators or matrices. So it's almost like you're doing matrix multiplication. And that's how you move from one state to the other. So this is where the idea of actually manipulating and controlling these elementary particles that obey to quantum physics basically generated the idea of how can we use them, how can we implement them. And the interesting thing is that we think of them as carrier of information. So these states, different states corresponds to actually, they carry information. They have different values, they have different states, and they correspond to information. Now, classically, the way we represented in the digital world the information with classical bits in our electronics is by setting two different values of on and off, on, off, 0 or 1. And suddenly now, we have particles that can carry much more information than the simple 0 and 1. It's actually the superposition of 0 and 1. You can have some of the 0 and some of the 1. In what sense? That means you can have maybe 30% 0, 70% 1, and so on. And now it opens up a whole space of possibilities. So this is a very rich system. So this is what we call now the qubit, the quantum bit. Okay. Another interesting difference between classical physics and quantum physics that was bothering the scientists early on is that we always expected that science is deterministic. That means we always thought that if I do a measurement, or if I want to locate an object or measure its speed or any other feature, I should be able to. That's not the case with quantum physics. When it comes to measuring, let's say, the position of an electron, it's very inaccessible. In fact, you can never tell exactly what an electron is. But you have another way of actually describing its location by what we call the probability distribution. We can tell where the electron most likely will be. Now, going back to this, what you see here is different clouds around the nucleus at the center. They correspond to where the probability density of finding an electron around the hydrogen atom. And so, and that corresponds, so different states will correspond to different distributions. So if you are in a particular state, for example, this one, most likely you will find it here, not in the dark areas. So this concept of probability of distribution is purely quantum mechanics. We're going from the deterministic science, deterministic physics, into probabilistic physics. And that's not a problem. Einstein was very, he totally disagreed on, he kind of didn't like this, and he said his famous statement when he was commenting on this. He said, God doesn't play with dice. I mean, it doesn't just can be anywhere. No, it has to be. Maybe we're missing something, but in fact, we're not missing anything. That's the way it is. That's how the law is. And what we notice that this discrete approach, this non-deterministic approach is actually very rich environment to do much more than what we thought in our classical systems. And the best example is this quantum list that we're now using. Now, going back to quantum computing. Quantum computing is mainly the engineering side of manipulating these particles. Okay, and you can tell me, okay, how can we go from physics, from interactions between particles, into doing some computational work? And for that, I tried to build a slide for that, but I think I can make it on the board here. See, I think I have some here. So, you guys see here too? So let me give you this example of a kind of weird shaped box. Okay. So it's a confined box with this weird shape. And then I'll ask you, I'll give you, let's say, some toy or the ball. And I'll give you, let's say, 8 balls. And I'll tell you, can you distribute these 8 balls within this box in a way that they are the furthest from each other? That means when I measure the distance between the total distance between any 2 balls will be the maximum possible. So this is a very hard problem to do, even with only 8 balls to do this. So there are different ways of doing it, but we can let physics find a good solution, the optimum solution, and very fast. Let's assume that these balls are actually magnets, and let's assume that they're only, 9, we have the North Pole and South Pole. Let's say they're only made in a way that they're only showing the south, one of the sides, south of the pole. Okay, one of the sides of it. What does that make them? Make them that they will never want to get close to each other. They will always repel each other. They will push each other. Then, if that's the case, all we need to do is to dump these balls here in this confined box. And they will automatically, they will naturally align or kind of find, each will find the best positions to be as far as possible from the other, because they just repel from each other. And we can just measure their location, find that optimum solution. And we haven't done really much work here. Now, if you read if you read their locations and you try to optimize, you will never find better location that they actually naturally evolve to, because they don't like to be next to each other. So this is exactly what we're trying to do with quantum computing. We're trying to let some physics, some physical interactions between our quantum bits to evolve to the solution that we're looking for. Of course, there are a lot of challenges there. I mean, the main challenge here is the engineering side of things, because we want to manipulate these tiny systems. We want to isolate these things, because these tiny systems, these quantum bits, I'll give an example. They could be photons, they could be atoms, but then they can be also very small metal particles that we call, or kind of loops or made of this pure metal called superconducting material, made of superconducting material. And they obey, of course, to law of quantum physics. And the idea is that to be able to control them, to interact with them, communicate. Most of the communication usually with these small particles is with electromagnetic waves. And in what sense? Interacting with them, actually measuring their state, identifying which state they are in, okay, kind of reading their energy. And that's the challenge. So it's significant. It's a challenging engineering problem. Most of the quantum computers, they will look something like this. And the whole system here, all of these wirings that you see, is mainly to transmit, actually connect, to transfer electromagnetic waves or radio waves to connect with the chip here. This chip is usually, that's the whole quantum computer. And Sprawley has, until now, the biggest quantum computer has about 5,000 qubits. So in about 2.5 inch by 2.5 inch, you will find 5,000 quantum bits that are connected in certain ways. There are couples of these. And that's why how it looks like. Now, we need to understand that these quantum bits, they are very sensitive. They can interact with everything around us, from vibration to cosmic rays to anything, any electromagnetic waves that exist. And for that, we need to isolate the system. So usually you will see these systems in kind of a small fridge where the temperature is kept at almost absolute zero, which is right now it's about 15 millikelvin. That's the best we can do. That's a 0. So 15 millikelvin, that's 0.0015 Kelvin. And that's about 100 times colder than the outer universe. So the coldest place on Earth, in the universe now, as we know it, is actually the chip of a quantum computer. So we made it that way because we need a total isolation from the environment, from any, when I said vibration, because temperature corresponds to vibration. When you warm things, the atoms start. And from also cosmic rays that can, so it's very, very well shielded and so on. And that's what we're doing about quantum. Now, to kind of elaborate on who are building what, and maybe you know these names. For example, Google is building its own quantum computer using these superconducting qubits. So they're basically metal loops that are very small, and they're made of this interesting material, what we call superconductors, and they obey law of physics, and they try to connect them. So every quantum computer is characterized by two main things, characterized by the number of qubits that they are using, and how well these qubits, how connected these qubits. So the more the connection, the better, the more complex of a system you can build on them. That's what Qubit, that's what Google is trying, that's what IBM is trying, that's what another company called D-Wave is building, and so on. Now, so the other challenge now for when it comes to quantum computing, and that's one of the things that we do, is actually you need to understand really how these qubits interact? How do they behave? And specifically when they are built in a certain way with certain connections, and project your problem, your computational problem into that. That's where comes the quantum computing or the quantum algorithms, because you need to understand your problem and then project it on this network of qubits, this system, to get to your solution. Okay. So let me tell you where we are today about that. So today we have these systems, but they're not big enough to build or to solve interesting computational problems. Not all of them. There is an exception. There is one machine, one quantum computer that is built to do a specific task, which is optimization. Finding the maximum or a minimum of some kind of function, which behaves exactly like what I said. So the whole system will interact and find kind of balance, or let's call it the minimum energy position where they are comfortable. There is no much pushing. So this is a Canadian company called D-Wave. So in our company we actually use this machine. It has about 5,000 qubits, and it has about 40,000 couplers. That means actually between any qubit, you have 15 connections to the other qubit. That kind of makes about 40,000 connections. So from an engineering perspective, it's very interesting, it's very complex, and they even struggle to, how are we going? Because what we want, we need a physical connection between one qubit and the other, with this. Now, let's say you have, so I'm just doing here, one qubit connected to 4. Now, how about they want one qubit to be connected to 15? And you need to place them, physically they are 3D objects, right? How are we going to do this connection? So it's going to get more and more complex, and then you're running out of space. And so they need to come up with different kind of engineering ideas to place them and build them circuits. Okay, I didn't answer the main question here is, why is it so important? Quantum computing will literally open the door or actually solve some of the problems that are called intractable, some of the problems that we can never solve. And we're still today. I'll give you an example. So I'm going to use an example from the application that we do. So at Qubit Engineering, what we're doing, we are actually designing wind farms. And when you're trying to build a wind farm, and usually you go and you have a site, you have a land of any kind of shape. Okay. And you have some data about the wind resources. Okay, the speed of the wind, its direction, the frequency. You can even also have some data about the topology of the land, so on. And then, so this is an input, and you're trying to find what is best place to place these turbines. And you want to place 20, say, and then here. So this is one of the very challenging optimization problems. Even though we've been building wind farms for like 3 decades or more now, it's still a very challenging problem. It's still a task that we're not really doing well enough. So the whole idea for our team is actually to find better way of finding the placement of these turbines. Now, to give you an example of how complex this problem is, let's say I don't need to place them on a land, which is a continuous space, right? It can be anywhere on that land. And I'll just say I have 100 possible sites. So that means instead of using a full continuous land, I'm going to just say, okay, I will have a grid with 100 possible positions, 10 by 10. Okay, and I want to place 50 turbines and these hundreds. So, I mean, it sounds okay, can't do it, right? Actually, we can't. It's almost impossible to do it. Why? Because if you want to find the best configuration, what you need to do, you need to go what we call brute force. That means you go and try all possible configuration. That means you take the turbine number one, place it here, number two here, and so on. And then you try. Now I'll do the one here, the two here, the three here, and so on. So if you want to calculate the number of possibilities for this case, you know, it's in combinatorial relation, it's like C50 from 100, right? So this is, can you guess how much that's, what's the value there? It's crazy. It's about 10 to the power of 31. So that's a number I don't even know how to pronounce. I don't know what's that number, right? So it's huge, it's possible. So we even actually calculated, so we have a collaborator at the lab, and we asked him, if you want to do this, to run this problem on the supercomputer at RNL Summit. So it's been decommissioned recently, they have a new one. They usually change or upgrade the computers every like 3-4 years. How long it will take? If we use the whole supercomputer, which is at some point, I mean, 2-3 years ago was the largest computer in the world, and try to run this problem, it will take us about 31 years just to do these kind of. So this is how hard this problem is. So it's a very challenging problem. Quantum computing can solve this kind of problems. When it reaches the maturity that we're working on, and get us a solution that we can never do. So I'm gonna show you one example of how we're using one of the features of quantum physics, for example, tunneling, to achieve a good solution. You know, an optimization problem like what we're doing, this wind farm design, mathematically or analytically can be represented in, of course, multi-dimensional space, but I'm going to do it just in 1D. Okay, something like this, some kind of weird functions of, you know, something like this, then go up, and our solution is supposed to correspond to the minimum solution here. That's the best solution we want. How are we going to get there using quantum physics? So what we do, the way we're building our problem, for this particular project, we project the interactions of these turbines on the wind farm to be represented by an equivalent interactions between the qubits. In what sense? That means we're creating kind of a quantum twin of the project on the quantum computer, and we replace these turbines with qubits. You know? So, and then we'll have the same kind of design, but now we're talking about qubits that are interacting in some sense, you know? And the qubits will interact in a way to find their minimum energy that can equivalent to what we talked about in this, placing these balls in the box, in some fine box. And the minimum solution is analytically somewhere here. However, the energy of the whole system, when I say the system, I'm talking about the qubits as one entity, one physical problem, one physical system, is actually could start somewhere here, or maybe somewhere here. And naturally, a physical system will always tend to go to its minimum. If you throw a ball in a kind of a well or kind of all like this, if you throw it, the ball will bounce back and forth, but then ultimately it will prefer to stay at the very bottom. That's the minimum energy position. The same thing for the qubits. It's a physical system. It will always look for the minimum energy. But if the current energy of the system is somewhere here, that's not the optimum solution. What the system will do will actually tunnel through this energy barrier and find the solution. That's how this quantum computer that I told you about called D-Wave is actually functioning. So it tunnels through this energy barrier to find an optimum solution. And that's why we get these solutions that classically are not really accessible, because it's very complex. So now the energy of the system, the whole system is a wave. This is an energy barrier, and then it will tunnel. That's how we get it. Does this make sense? Any questions? Yes.
Your problem of attaching qubits to other qubits seems to be an optimization problem. Could a quantum computer solve that for the maximum number of qubits you could attach another one to?
So we have challenges. First, we depend on the machine that you're using. We depend on the coupling that you have. And for example, if we use this D-Wave machine, right now we're limited to 15 couplings between one qubit to the other. And sometimes maybe you need the further interactions. For that, sometimes you need to sacrifice some of the qubits instead of being involved in the interaction. They will be used as messengers just to connect. And what you end up doing, you end up using more qubits than you actually have or you can afford. And that limits the size of the problems you can do. Okay. So that's why now the race in the US, in Europe, everywhere in the world is to build bigger systems with more connectivity so we can solve more interesting problems.
One more question.
Go ahead.
So, Emma, do I understand that the geometry of how you configure the qubits and how they're connected, that determines the kind of problem you can solve?
Yes, absolutely. Absolutely. And that's why I have to adapt to, so I have to work with the manufacturer to understand their system so I can build my problem in a way that can use the most of it. Of course, they do it in a way where they tell you, you can build your problem, but it's not going to work because you will end up sacrificing some of the qubits to be like messenger or connection. We call that chain. So that's one thing I wanted. So there's another point I wanted to share. Okay. So basically, that's where we are today. Technology is all about building more of these quantum computers, bigger ones with more coupling. And as I said, they need to be held at a very low temperature and totally shielded. So one of the optimistic opportunities to build a simpler quantum computer is to use photons, light. So because light doesn't need to be, or photons, they don't need to be held at a low temperature. That means we can use them at room temperature. And they can be a small system. If we achieve this kind of photonic quantum computers, we will have a photonic quantum computer in the laptops. So we're still far from there. The technology is still not ready. And that's because it's hard to build these interactions between these photons. It's hard to build these entangled photons, even though we make them. Now to create two entangled photons, you need to have a setup on the table, an optical setup on the table. So it's still big. things are improving and changing, and a lot of the work has been done at RNL and other labs. You know? So the one important message I want you to take away from the day today is what we're talking about and what you are reading is this is all about the different states of qubits. That's why it's interesting to use quantum computing, because one quantum bit has different states, and that means it can carry a lot of information. And that's why we call it quantum information science. So how can you manipulate this information from an engineering perspective, but also from an algorithm perspective, from a theoretical perspective. So information is key here. And these elementary system or these interesting objects, small microscopic quantum objects, they carry information and they change information through this interaction between wave functions. So basically everything around us, everything that makes matter is built around carrying information. So I want to add now, I want you to think about this. This is a very interesting concept that I've been exposed to a few years ago and still intrigues me and very interesting. So you know how pictures are made, pixels. No, if you have an old phone, you will have smaller number of pixels. The newer your phone, the better, because you have more pixels, right? The resolution is better and so on. How pictures are made, you know, with these different colors. If you look at the tiny pixels, they just have colors. And probably they have, like they're made of like red, blue, and green, the elemental colors and so on. So every pixel carries some information, right? And that's how we, now how we go from here to here, we multiply by certain factor, the number of pixels. And suddenly we see even a better picture. But if you zoom in, even in the higher resolution one, you will end up with this. You'll see kind of pixels. At the very end, when you zoom in, it's just a value, it's just a color. At the individual pixel level, you just have one color. The collection of these pixels give you that information, right? That's what makes the macroscopic picture that we see. So this is a question, or this is a suggestion. If, let's say, together we build an image of 1,000 pixels by 1,000 pixels, that means we have 1,000,000 pixel total. And we know that every pixel can have a color. And then we start changing the colors, randomly changing the colors of each pixel. And we try to do kind of cover with the same kind of idea of brute force, cover all possibilities. In one of these possibilities, we can actually see a picture of this class sitting exactly how you are guys now. Is that a possibility or not? It is, right? What does that mean? Even maybe in a few minutes you'll be leaving the room, which is corresponds to the future for us from now. In a few minutes is the future. It's also one of the possibilities that you can have on this, right? So basically, I mean, that's why I said that you need something to think about. You can, if you have a way to cover all possibilities, you can look at the past and the future of anything. And think now that we add, I'm only here talking about the two-dimensional picture. Think that we add additional dimensions. We add voice, or we add, let's stick to image and voice. That means we can build a video or scenario of anything that happens anywhere, just by brute force and going through it. What does that tell you? do we exist in the future, in the past, or, you know? So, I think I will conclude with this. I'm happy to take any other questions.
What questions do we have, Dr. Salhi?
Question.
Yes.
So, with like, new points, so, interactive optimization.
Correct.
Is that mainly what it's used for? What about intractable problems with other types?
So, our company focuses on optimization problem, but you can do so many things. I would say every problem or project you work on is going to be at this point very specific, because one of the things is that you need to adapt to the hardware. We're still at the early stage of developing the technology, so there are many ways of doing things, but you can't do everything. So you have to pick your your discipline and what you want to do.
That makes sense.
I have a sort of easier question.
Sure.
If someone in this room was interested in, taking a path that would lead to working in this field, what kinds of things would you suggest they do and study and
Okay.
think about?
So that's a very good question. So I think when studying physics in general, people or students they are struggling with. There are two things that you need to learn. You need to understand phenomenon that's happening or you're discussing or being taught. That's one thing. You need to understand how the different elements are connected, but there is that kind of understanding, and there is also the mathematical representation of that phenomenon. So a lot of people, they have the imagination to understand the physics side, but then when it comes to dealing with equations and the math representations, they may struggle. So for quantum physics, it's very important to kind of get used to linear algebra, the manipulation of matrices. If you have that from a mathematical perspective, and of course you need to understand the kind of be a little bit imaginative about the phenomenon, what's happening. Connecting both of them will give you a good picture of what's happening. So math is the language of science, in the sense that you can use it to interpret or to kind of represent what's happening in the real world. Did I answer your question?
So you're saying do math?
Absolutely, absolutely. I mean, if I have time, I will learn more math. And in fact, we're reaching a point where some of the physics discoveries are actually the result of mathematical solutions. I'll give an example. Negative numbers. What are negative numbers? We don't really think of them. We don't really use them, right? In fact, we use them, but kind of didn't make sense in the real world. What's a negative number? But I'll go and explain. In some of the equations that we've been solving, we get negative energies. But that's even harder to comprehend. What's a negative energy? And in fact, now, and not now, but decades ago now, negative energies corresponds to what we call on-type particles. The only interpretation of on-type particles is that they have negative energies. So that's where the math, in classical physics, when you get a solution that is negative, say that's not a solution that I can take, I'll take the positive one. You're solving just a quadratic equation, you have a positive and negative solution. But in physics, that's not something that you throw away. actually it has the corresponding physics representation, which is on-type particle. On-type particle is totally the opposite of a particle. And if they collide, they will anneal, they both disappear, and they will generate pure energy. So electron has an on-type particle, positron.